All right, we're going to name that transform toolkit function. And we're going to start off with this weirdly shaped v function, which we all know is the absolute value type function. And the generic form of this function is y equals a times the absolute value of x minus h plus k, where hk is something we call the vertex. All right, and in order to come up with the equation of this toolkit function, the vertex on here is 4, -3, if we can't see it. And this point here I gave you was 0, 5. All right, so hk was given to us, which is really nice. So we can say that y equals a times the absolute value of x minus 4 minus 3. And now we need to solve for the stretch factor, which is a. So we can say using the point 0, 5, we put this in for the x, 0, and y is 5, so we plug that in. So we can say 5 equals a times the absolute value of 0 minus 4 minus 3, and that'll give us an equation 5 equals 4a minus 3. Adding 3 to both sides, we get a equals 4a, and a will equal 2. And so our function name for this absolute value function is going to be y equals 2 times the absolute value of x minus 4 minus 3. So we have named that transform toolkit function. All right, so let's try a different one. Here we go. This one is a quadratic. And if you can't see for the video's sake, this is the point 2, 3 up here. This is the point 4, 0. This point here is the origin 0, 0. And this is a generic, this is an upside down quadratic. And there are two forms that we could use to find the equation of this quadratic. And most people would start with vertex form because they gave us the vertex here. And vertex form, the general form for that is y equals a times x minus h quantity squared plus k, where hk is the vertex. So we know the vertex is 2, 3, and we can use that and say y equals a times x minus 2 quantity squared plus 3. And now we have to solve for a, the stretch factor. And we can use either point here that we were given. And most people would choose 0, 0 because that's a really nice point. Most people like to plug in zeros. So y is 0 equals a times 0 minus 2 quantity squared plus 3. I'm going to move the 3 over. We get -3 equals, and then -2 squared is 4. So this will be 4a. A is going to equal -3/4. And so the equation of this quadratic is going to be y equals -3/4 times the quantity x minus 2 squared plus 3. And we have named that quadratic, or named that transformed quadratic. Now, we all expected, I hope, to have a negative leading stretch factor because this quadratic is upside down. Well, believe it or not, there's another form that we could have used to come up with the equation here, and that is factored form. Now, this one here is the generic for vertex form. Forgot to write that up there. Oops. All right, so let's try factored form. Well, the generic formula for factored form is going to be y equals a times x minus p times x minus q, where p and q are the zeros of the quadratic. And factored form is really nice to use when you are given the factors but no vertex. Now, I gave you guys the vertex in this example so that we could use vertex form and factored form. But I would use factored form only when I had these two zeros in a point like over here or somewhere other than the vertex. But we'll use it in this case just to illustrate the point. All right, so the zeros are 0, 0, so I would write y equals a times x minus 0, which is the first 0, times x minus 4, which is the second 0. And we could simplify that to y equals a times x minus 4. And now we can use one of the other 2 points to help us out. Oh, actually, we can't use the zeros to help us. So we're going to use the other point we were given, which is 2, 3, because a 0 would zero this out, which would not be helpful. So we're going to say using 2, 3. Oops. We can plug that in. We can say y equals 3. And we're left with a, and x is 2, and then 2 minus 4. So this is 3 equals a times 2 times negative 2, which is 3 equals negative 4a. A equals negative 3/4. And we expected that again because we'd already solved for it here. So the factored form equation would be y equals negative 3/4 times x minus 4. And that would be the factored form equivalent. All right, now if I don't ask you what form, you're free to put it in vertex form, standard form, or factored form. All right, let's amp it up a little bit and name this transform toolkit. Well, this one is, believe it or not, a cubic function. And I'm giving you some zeros here. That's negative 3, 0. This is 2, 0. And this point here is 4, 0. And the point on the curve that is going to help us out with this equation is 0, 12. So the only way to do this cubic is in factored form. So we're going to say this is y equals a times x minus p times x minus q times x minus r, where p, q, and r are those zeros. And we can rewrite this equation as a times x plus 3, because we have to use the opposite here to make it a factor, and then x minus 2 times x minus 4. And using the point they gave us, which was using 0, 12, we can solve for the stretch factor a. So we know that y is 12, so 12 equals a times, well, when x is 0, we just get 3 times negative 2 times negative 4. And if we multiply 3 times negative 2 times negative 4, we get 12 equals negative 24a. A equals negative 12 over 24, or negative 1/2. Or I'm sorry, that shouldn't be negative. It should be positive, right? Because a negative times a negative is a positive. Got to watch out for my signs there. So that's equal to 1/2. So my cubic would be y equals 1/2 times x plus 3 times x minus 2 times x minus 4. And this is in factored form for the cubic. And if we wanted to, we could multiply that all out to get standard form. And but we're not going to do that for the purposes of this video, because I know that you could multiply all that out and get that in standard form. So this would be in factored form with the stretch coefficient of a equaling 1/2. All right, moving right along. Let's try another one. This is a toolkit function that has been transformed, and this one would be a square root function. And the points, which you can't see here, are 1, negative 4, and negative 3, 2. And the generic form for a square root function is y equals a times the square root of x minus h plus k, where hk is the vertex, but it's only half of the vertex because we had to restrict the domain for it to be a function. So we know we're given hk, so we can say that y equals a times the square root of x plus 3 plus 2. And then we have to solve for the stretch factor a using the other point. So we're going to say using the point. Oh, actually, this is 1, negative 6. using the point 1, -6, we're going to get -6 equals a times the square root of 1 plus 3 plus 2. So I'm going to move the 2 over and get -8 equals the square root of 4, which is going to be 2a. A equals -4. So we can say our equation is y equals -4 times the square root of x plus 3 plus 2. And there we have written an equation for our transformed toolkit function of the square root of x. Now, I did a chart here just for extra practice, and we're going to add 2 lines to this chart. We're going to add a line for the inverse of f, and we're going to add a line for the tricky one, which won't be tricky to you guys because I can't fool any of you. Let's say I want to do f of f inverse of x. And we'll make that our last line because we have to be a little bit more exciting than these upper rows here. All right, so what are we doing here when we do our table? We're going to take the f of x here and multiply it by -1, or by making it the opposite. So we're going to make every one of these f of x is the opposite of what they are. So the first column is going to be 4, 1, -2, -3, 0, 3, 6. That was easy enough. Now we're going to take every f of x in this row and we're going to subtract 2 from it. So the first one will be -6, -3, 0, 1, -2, -5, and then -7. Oh, no, I'm sorry, -8. And now we're going to take all those y values of f of x values and add 2. So this will be -2, 1, 4, 5, 2, -3 plus 2 is -1, plus 2 is -4. Now we're going to make x the opposite of what it is. So if x is -3, f of -3 is going to be f of 3. So I go to the f of 3 column and I put -6. So what we're doing in effect is taking this these set of y values and flipping them. So we get a -6. F of -2 means I'm going to go to the 2 spot and put what you get for f of 2, which is -3. And then 0, 3, 2, -1, -4. All right. F of x minus 2. That means I'm going to take this x value if I'm given and subtract 2. So I get f of -5. But I don't have a -5 in the x column. So I'm going to put a dash. Then I'm going to do f of -2 minus 2, which is f of -4, which I don't have in that column, or that row. I don't have a -4. And now f of -1 minus 2, which means I'm going to get f of -3, which is going to be -4. So we're going to have -4. And then I'm just shifting everything to the right by 2. I mean, by 2. I'm going to use all these values and move them right by 2. This next line is taking all of the y values and multiplying by 2. So we're going to take these y values, f of x's, and multiplying by 2. So we're going to get -8, -2, 4, 6, 0, -6, and then -12. The next row says we're going to take all the x's and add 2. So this is going to be -3 plus 2, which is f of -1. So I'm going to start in this column and put 2 here. And so in effect, we're shifting all of these y values to the x's to the left by 2. So we're going to go 2, 3, 0, -3, -6. And these last 2 are blank because I'm not going to have an f of 2 plus 2, which is 4. I don't have a 4 in this column here. Now this says take the opposite of f of x and divide by 3. Well, I've already taken the opposite of f of x in the first row here. So I'm going to divide everything by by 3 because I've already done the first step. So this one would be 4/3, 1/3, -2/3, -3/3, which is -1, and then 0, and then 1, and then 2. All right. Last but not least, I am going to do this row first because it's actually going to turn out to be the easiest row. So this row here says take the function and compose it with its inverse. Well, we know back when we were talking about inverses that if you take a function and its inverse and you compose them, you just get x, because what you're doing in effect is canceling out these operations. So this whole row is going to be nothing but the x value. So we're going to put -3, -2, -1, 0, 1, 2, 3, and we're done. So that was easier than it looked. And then last but not least is the inverse row. And I like to do it by creating my own inverse little chart here because it helps me. So I'm going to put x and f inverse of x. And so when we find the inverse of something, what are we doing? Well, you're switching the x and the y. So I'm going to take all the x values here and put them in the y for the inverse. So let's do that. That's going to be -3, -2, -1, 0, 1, 2, 3. And then I'm going to put all of the y's in the x column. So I'm going to put all of this row in there. So it'll be -4, -1, 2, 3, 0, -3, 6. And now we're going to say, let x equal -3. Well, this x is -3. Do I have a y value in the inverse? I do, which is 2. So I'm going to put a 2 here. Then I go to x equals -2. Do I have any x that's -2? The answer is no, so I don't have to put a dash here. What about x is -1? Well, I do have a -1 and the y is -2, so I'm going to put a -2 here. And 0, look at that, I have 1, so we'll put a 1. F of 1, I don't have a 1 here, so that's going to be a dash. F of 2, do I have a 2? I do, which is -1. And then 3, I do, which is a 0. And I just wanted to do a chart and show an inverse and maybe a little bit more of a challenging one that turned out not to be a challenging one, so that we could review our functions, transformations, and chart work. So that's all I have for the notes, and we will see you again another time. Thanks.